All right, 3.2 started last time. We're going to continue here. We're in the middle of taking a look at some different algorithms, which are ways of doing things, right? So we're doing ways of doing or algorithms for addition. And we had encountered a couple last time, I think 3. Yeah, and we're on column addition next. All right, so column addition gives us the ability to actually add from left to right. Okay, that's what it really does. That's its benefit. So we're doing an example where we have several numbers. If you just have a 2-digit number, it's not really like all that useful, but when it becomes longer digits, it's a little bit more of a usable algorithm. So we're doing 1534 and 3218. And the way that this works is you think about the 1 and the 3 in terms of their place value. So the 1 is actually a 1,000 and the 3 is a 3,000. So I'm going to write down what I'm thinking next to it. It's not what the child would actually write, but what we're really thinking of here is that this is 1,000 plus 3,000. And so in a very real sense, you add these together and you get a 4 lined up right underneath them. And it's the equivalent of writing 4,000. So you can write the 4 and just leave it, or you can put the zeros in there as placeholders to remind yourself like that it's lined up properly, okay? Your choice. Do the same thing on the next column. So the 5 and the 2 would be a 7. Okay, so again, you're really doing 500 plus 200. And again, the stuff in the parentheses is not what you would actually see a kid writing down, okay? And then you have the 3 and the 1, so you have a 4 here. And again, that's really 30 and 10. And then the most interesting one's the last one, because they don't add to a number that's a single-digit number. All the others have been a single-digit number, right? It was a 4, a 7, and 4. So this one actually says that we have 4 plus 8, which is 12. And so it has to line up with the 2 directly underneath it, and so the 1 just gets pushed over into the next column. But that should make sense. That's the tens column, and that's what that 1 means. But that's how it gets lined up. And then you do the same thing here. It's just that when you add here, again, you can go from left to right. You end up with far fewer places, potentially no places, where you're going to end up with a number that's a 2-digit number when you add down. So if I add down here, the 4 is a 4, the 0 and the 7 are 7, the 4 and the 1's a 5, and the 2 is a 2, and we're done. Okay, so longer process, obviously, but it allows us to move from left to right, and it allows us to sort of focus on a piece of it at a time instead of all of it at the same time. All right, lattice algorithms, the next one. The lattice algorithm has us actually taking the same values, and we're set up kind of like the last one, 1894, 32, 18, and we create a box underneath them. And the box is split into 4 because it's a 4-digit number. So however many digits are is what you would have. So these aren't lining up very well. Let me make my numbers just a little bit bigger so they line up a little bit better on my boxes. That's better. And you're going to split your boxes each into halves. Try that again. That's better. Okay, so they get split in halves along diagonals. And again, we can move from left to right, or you can move from right to left, it doesn't matter. But the 3 and the 1 would become a 4, and you write the 4 down in the bottom corner, like so. The 8 and the 2 make 10. So it's a 2-digit number, which means you've got a top number and a bottom number, right? There's the 10. The 9 and the 1's also a 10, and then the 8 and the 9's a 17. So they get written in their kind of, I'm sorry, it was not 8 and 9. I was too far up my screen. 8 and 4, which is 12. Sorry, 12. And then what you do is you sort of extend, whether you physically do it or whether you just sort of mentally extend them. You're extending your diagonal lines and you're going to add up along diagonals. Now, it does matter at this point that you start in the bottom right-hand corner. Okay, so this number is a 2. I have my 1 and my 0, that's a 1. I have another 1 and 0, that's a 1. And I have a 1 and a 4, and that's a 5. And if you did have something that added up to a 2-digit number, like let's say a 12 showed up there, you'd write the 2 down and you'd carry the 1 over to the next diagonal column, just like we would do in the standard algorithm, okay? It's a different visual. It lines things up in a way that makes it feel like it's still in the right column, right? Like my 12, but it gets added to the tens digit, the 0 here, right? So this is lattice. Opposite change. Opposite change is interesting, and we'll encounter it with a different name a little bit later. So with opposite change, we have 488 and 231. And what you're doing is your goal, and write this down, your goal is that there is no regrouping. Or no carrying in this case. That's the goal. No regrouping. So here's how you do that. In the doing of that, you're trying to take numbers and you're trying to change them into things with lots of zeros, which is kind of what happened with our column addition, right? We wanted to turn things into having lots of zeros by focusing on one digit at a time. So it's much like that, but it's done in a different way. You look at the two numbers and you kind of ask yourself from the ones place, what's the easiest way that I can turn one of those numbers into a zero? And we're typically working with addition because we're still working with addition here. So the easiest way to turn one of these numbers into a zero would be to add a 2 right here. Agreed? If I add a 2 here, then the 488 will become 490. Yep. Now, you can't just go adding 2s. Right? That's not appropriate. So if you add a 2, you also have to subtract a 2. So we take away a 2 down here. They're small numbers that we're working with, which makes the addition or the subtraction pretty straightforward. You can do a kind of accounting strategy. So 231 moves down to 229. And now if you take a look at this, I don't have to carry anything, right? I don't have to regroup anything if I add the ones column. I have a 0 and a 9. But that's not true about my tens column now. I have a 9 and a 2, right? So I do the same thing again. And technically you could do it to either column. It's going to, or not column, either number. But it's going to be on this one the same number. Like we have a 9 and the first number is still misplaced, right? So what would I have to add to 9? Just think 9 with me to get the 9 to become a 0. I need a 1. But it needs to be in the tens column because the 9's in the tens column. So I'm not really going to add a 1. I'm going to add a 10. So I'm going to add 10. And again, it could have been to the bottom number, but the 9's the one that made sense. So I'm doing it there. And if I add 10, I have to subtract 10. So my 490 becomes 500, and my 229 becomes 219. And the first place where I don't have to do any regrouping if I were to add them is when I add them. Okay, so at this point, if I had had two numbers still like the 5 and the 2 that added to something more than 10, I'd do it again. But I don't have that here. At this point, I can add without any kind of regrouping. You could even move from left to right if you wished. This would be 719. Opposite change. Okay. The next one, scratch algorithm, you'll notice that the problem is set up quite different than the other ones we've done. I don't have a 2-digit or a 3-digit or even a 4-digit number. I have a list of numbers, like there's a bunch of them, right? Okay, so we're going to write them vertically. And what we're going to do is we're going to add kind of like we would do with a standard algorithm, but we're going to make it so that we never add together anything that's more than a 1-digit and a 1-digit number. So let me show you what I mean. We're going to start at the top, okay? So I have 4 plus 8, and what is 4 plus 8? It's 12. Well, if I get something that's bigger than a 2-digit number, like it's got a tens digit in it, I'm going to make a scratch through the number where I got it, and I'm going to stop thinking about it as a 12, because I scratched it, and I'm going to think about it as just the units digit I got, which is a 2. So I'm going to sort of jot this down on the side. Again, the student's work wouldn't look like that, but I want to remind you where we are. We're at a 2 at this point, because I've scratched. It's almost like the scratch is like representing the 10, right? Okay, so now I add the 2 with the 9, and I get 11. But that's bigger than 10 again, or 10 or bigger. So I scratch again, and instead of remembering the 11, I remember the 1-digit part of it, which is the 1. So again, normally I wouldn't even be writing these numbers at the side if I were doing the problem. I don't want you to see what I'm doing a little bit better. So feel free to not write them down when you're working these problems out. And then I'm going to add my 1 and my 7, and it's in 8. And we have an 8 showing up at the bottom then. Okay, it's not a 2-digit number, so I can just write it down. Then I count my scratches. How many scratches did I make? 2. That's the number I carry to the next column. So the 2 gets carried over. And then I'm going to repeat the same thing with the tens column now. So 1 plus 3 is 5. 2 plus 3 is 5, is what I meant to say. Starting at the top. 2 plus 3 is 5. That's a single digit number, so I keep going. So now I have 5 plus my 1 is 6. Plus another 6 is 12. It's too big. So I scratch. And I'm going to remember the 2 in the number 12. I'm just going to jot it down over here. And then I have a 2 and an 8, which is a 10. So I scratch, and the 0 is what's left. That's what gets written down at the bottom. How many times did I scratch in the tens column? 2. So the 2 gets carried to the next column over, but there's nothing in that column, right? It's empty. No, there's no other hundreds digits. So the 2 just comes down to the bottom, and I have 208. So all it's really doing is it's keeping you from kicking, like when I got to the 12 in there and having to add 12 to something, right? It's trying to sort of push us back into those multiplication, or not a multiplication, addition cards that you learn, right? You don't learn addition card, you might with 12s, but you don't learn addition cards for 2-digit numbers on a standard basis, right? I don't have an addition card memorization for 18 plus 12. Okay, I don't have that, right? I can do it, but it's not something I would have seen as a rote memorization kind of thing anywhere along the way. So this is sort of moving us back into that and keeping single digits as the focus. All right. So what we're going to do next is we're going to consider how this works in other bases. And then we're going to do some mental math. Okay, so in other bases, and I'm going to try and show you a couple of different options for how to think about this in other bases, like a couple of the different algorithms and how to do them. So we're going to do 3, 4, base 8, and 1, 7, base 8. And the first way I'm going to do it is just our standard algorithm. So the one that you're most familiar with, probably. Okay, so since this is in base 8, there's no 8s and 9s in base 8, right? We cap out at 7. So when I add a 4 and a 7 together, how much is 4 plus 7? Like, what is it? It's 11, right? That's more than 8, right? It's more than 7, I should say. How many more than 7 is it? It's 4 more, isn't it? So if I were to sort of take those 11, so imagine I had those 11 cubes now, right? 11 of the single little Lego kind of pieces. And I took 8 of them and I grouped them together because this is base 8. How many would I be left with? I'd be left with 3. I'm grouping 8 because I'm in base 8. Okay, so I'd be left with 3 over. So that's the 3 that gets put in the bottom here. It's the amount that's above your base. That's what we do when we get 13 normally, right? When I get 13 normally, I put the amount over 10, which is a 3, down, and then I carry 1 to the next column. I regroup it. So I'm regrouping this one as well. And then I do the same thing in this column. 1, 3, and 1 is 5, and 5 works just fine for us to add together. So it's 53 base 8. 53 base 8, excuse me. Let's do, I don't want to do the one that's on my paper. Let's do the expanded algorithm. So the expanded algorithm would say that I have 3 8s and I have 4 1s, and then I have 1 8 and I have 7 1s. That's what the expanded algorithm would look like. When we wrote ours, we wrote them a little bit differently because 3 10s we could just write as 30, right? So this is 3 8s. We're just writing it as 3 times 8. So we're going to add the columns together. So this is 4 8s, and it's 11 1s. And then we break the 11 apart into what they are in terms of it being, okay, here's my 4 8s still. We break the 11 apart into it being 1 8 and 3 1s. And then my total number of 8s is 5 8s and 3 1s, which is 53 base 8. That would be an expanded algorithm approach to this. Is that right? Okay, we have one more like this. We have 1 2 1 2 base 3 and 1 1 2 base 3. So again, I'm going to do the standard algorithm first. And then I'm going to do a different one. And it's not going to be the same one I did last time because I want to see another version of it. Okay, so we start with the ones column. I have 2 plus 2, which is 4, right? How many groups of 3 are there if I have a number 4? There's one group of 3, so I'll carry that 1 over. And how many's left? 1. So the 1 gets rewritten. Okay, in the second column, I have 1 plus 1 plus 1, which is 3. That's a group of 3. So I carry it over, and I have nothing left to write down after I've sort of regrouped it. I have 1 plus 2 plus 1, which is 4, which is one group of 3 with 1 left over. And then I have a 1 and a 1, which is a 2. And always at the end, oops, we need to write the base, which is 3 down. Okay? All right, so we're going to do the lattice method on this one. These have up to 4 digits, so I'm going to do a 4-digit lattice. I have 1, 2, 1, 2, and then 1, 1, 2. And I split my diagonals like so. Okay. So again, we can move from left to right or right to left, doesn't matter. We'll go from left to right since we have the ability to do so. So in the far left column, I just have a 1, right? So it just gets written down here, 1. The next column over, I have a 2 and a 1, which is a 3, but I'm in base 3. So that's 1, 3, and 0 left over. The next column, I have a 1 and a 1, that's just 2. And the next column, I actually have 2, and 2 is 4, which is 1, 3, and 1 left over. Okay, everybody good? Now we're going to extend our diagonals, and we're actually going to see a place where we have to do some regrouping within the lattice. We didn't see that last time. So we start in the bottom right-hand corner. This is a 1, so I just write my 1 down. But in the second column, or the second diagonal, I have a 1 and a 2, which is a 3. I have to do regrouping in the middle of this, which means I move, this over to being 1 over here. I'm carrying, if you will. And I have 0 3s left over. It's one group of 3 that I had. The rest of them I can just do straight away. I can do 1 and 0, which is 1, and 1 and 1, which is 2. And I get 2, 1, 0, 1, same as before. Okay? It feels a little awkward to add another basis. This is one of those places where, why are we doing it? We're doing it to put you in a position of your students, to feel a bit awkward, because these are unfamiliar bases to you, just like to some degree, base 10 is a little unfamiliar to your students because they haven't been working with it for 20-something years like you guys have at that point, right? It just haven't. So it puts us in a little bit of an awkward position, and that's on purpose. Okay, we're going to look at some mental math and some approximation, I believe, is the last thing on this section, yeah? So mental math, there's some different strategies that we're going to look at. The first one is adding from left to right. So we've got an example. We're going to use 46 plus 38 on several of our examples. And we're going to do this first one, which is adding from left to right. So we take the number 46. And what we do is we add the leftmost number and the other value to it. So in other words, 38, we're just going to add 30 to start with. So 46 plus 30 is 76. And we do the same thing with the, I didn't mean that right. I'm sorry, I got off of my line. I'm looking down at the next one. Just put a line through that. We'll come back to that idea in a second. That's the next one, which is breaking up and bridging. Here's what we do, taking it back. 46, we are going to break 46 up into 40 plus 6. And then we break up our 38 into 30 plus 8. So this actually feels a lot like doing the expanded algorithm that we did before, much like that. And we add these together. So I have 40 plus 30, which is 70. And then 6 plus 8, which is 14. And then I end up with something, always here, I will end up with something where parts of it have some zeros. And that's what makes it easier to do in the last step, is that there's some zeros involved. So adding 70 and 14 together means that I'm going to have 84. Okay, and it's easier to see because there's zeros. Okay, let me go back to breaking up and bridging now, since I was trying to do that one earlier. And let me preface it by saying we're going to break up the 38 into 30 and 8, which is what I said but hadn't written because I was in the wrong method, all that good stuff. All right, 38. And we take the 46 and we add the 30 to it. Technically, you could add the 8 to it first if you wanted to. It doesn't really matter, but the 30 is where we're going to start. And so 46 and 30 would be the 76. And then you add the 8 after that. And again, I don't have zeros on this one to make it easier to work with, but I am still adding a single digit to a double-digit number instead of two double-digit numbers. Okay, so the thing about mental math is that it's supposed to be something you can do in your head. Okay? Obviously, we're writing things down, but we're doing it for two benefits. Number one is that I want you to have notes to go back and look and know what you did. I mean, so that seems reasonable. But the second reason is because I can't see what's going on in your head. And so I want you to be able to write me down some notes about what you're doing so that I know how you're thinking about the problem. Cool? Okay. This next one we've actually seen before as well, or at least a very near version of it. It's called trading off, and it's really the same thing as opposite change. It's just that it's done typically with small enough numbers you could do it in your head. Okay? So we have the same numbers, 46 and 38. So I'm going to write them down. And the idea is to try to get something to become a 0. So which of the numbers is closer to becoming a 0, the 6 or the 8? The 8, okay? What would I have to do to the 8 to make it become a 0? I'd have to add 2. But I need to do the opposite to the other number, so I'm going to subtract 2. So this gives me 44 and 40. And then 44 and 40 would be 84. I don't need to do a second step because they don't add up to too many, right? Just like when I was looking at opposite change before. All right, I mentioned the next one last class period. It's called computational or compatible numbers. I didn't call it that, but I mentioned the process. What compatible numbers is it's actually grouping things so that they are very nice things to add together. So do you remember when we did that strategy where we talked about it making 10, right? Where you're trying to take numbers that make 10. That's basically this is the same thing, okay? So you're looking for things that very nicely add together. So do you see any numbers in here that very nicely would add together? They're not going to make 10, they're going to make 100. 70 and 30. So these two are very nice to add together. And 60 and 40. So we have 250. And we're allowed to do that because we have properties of commutative and associative that say I can rearrange orders, I can add things together that make sense or convenient to add together, and I'll get the same thing as if I had done it sort of a harder way. Good? Okay. But maybe you don't have compatible numbers, but you maybe could. So this one is making compatible numbers. You only see 2 numbers listed. What we want to do is we would like to change one of them to be compatible with the other one instead. So you can either take the 68 or you can take the 35. It doesn't matter which one it is. I'm going to take the 35. And you can think about how could I change 68 so that it becomes something that's really nice to add to 35. So what number is nicer to add to 35? Not 70, 65. So why am I saying 65? Because notice over here what I was trying to do is make the number 100, right? So how do I make the number 100 if I have a 35 to start with? Well, I have 65. So I take the 68 and I make it 65 and 3. I could have done this as well with the 68 if you wish. I could have done 68 and taken the 35 and made it a 32 and a 3. So 32 and 68 add to 100. Okay, so you're trying to find something that adds to 100. Some of them are a little bit more obvious on which one's sort of convenient to do it with, and some of them it's sort of either way is fine. Either way, these two then make 100, and you get 3 more, so you have 103. Or these two would add to 100, and then you'd get 103. Yeah? Okay. Please mark the fact that mental math and computational estimation are not the same thing. They feel similar, but mental math gives me an exact answer, like it's correct. Computational estimation is going to give me an approximation. It's a pretty good number we could probably live with. Are you with me? All right, so this is like my kids doing Bible verses, and when they want them word perfect, and they miss a word, one of the ladies at our church will say, "It's good enough to live by." right? You missed a word, so what? It's good enough to live by. Approximations are generally like that. It's good enough. We're close enough. That's what an approximation does for us. Okay, so the first one we're going to look at is called front-end estimation with adjustment. Specifically, this with adjustment part is the important part. So there's two pieces here. There's a front-end estimation piece, and there's a with adjustment piece. Okay, so let me talk first about what front-end estimation is. We talk about this as well in proportional and statistical reasoning, so you might have seen front-end estimation there before. So front-end estimation takes the first digit, and it zeroes everything else out. Okay, so 332 is just written as 300, 462, 400, 225, 200. That's it. That's front-end estimation. We add them together, 4, 5, 6, 7, 8, 9. That's 900. Okay, that's front-end estimation. All right, the with adjustment part takes a look at what we didn't actually get to include, these numbers. And we can do this with a 3-digit number like we are now, or it could be a 4-digit number, doesn't matter. You still use just the first digit, and then you consider whatever else is remaining afterwards. Okay, and the goal is not to do the same thing again. We're not going to turn 32 into 30 and 62 into 60 and 25 into 20. That's not what we're doing. That'd just be another front-end estimation step. Adjustment actually means that we're going to be looking for or trying to make compatible numbers. But we're doing it sort of as it's pretty close to. So if you take a look at 32 and 62, for example, or you could even say the 62 and 25, but the 32 and the 62 is a little bit closer. 32 and 62 is almost 100, right? So you're taking these two and you're saying, well, this is approximately 100. And then you can keep the last value, if there's only 3 digits like there are here, the same. Or you might end up having to group, 2 sets of things together to try to get to be 100 or something like that. So we have the 900 from the front-end estimation. We have the 100 from the adjustment. We have sort of the 25 left over. And we're combining these three. What will I get? 1,025. And because we're doing estimation or approximation, you might end up grouping things together slightly different than someone else, and your answer might actually look a little bit different, and you're both okay. Okay? So don't agonize over, does mine look like theirs? How they grouped these two numbers together. As long as the grouping still makes sense, it's totally cool. All right, the next one is much like that. It's called grouping to nice numbers. So again, you might group a little bit differently, and you might get a little bit different answer, but they're all going to be in the same ballpark. We're looking for numbers that are like approximately compatible, kind of like the adjustment thing there. So what two numbers here would you look at and say, that's about 100? All right, 35 and 64. Or you might do 35 and 71. Right? I'm going to do 35 and 71. It works out a little bit nicer for the other numbers that are present here. 35 and 71 are about 100. What else is there?
42.
Yeah, and that's kind of why I did it that way. The 42 and the 64 is another one that's about 100. And then there's one left over in the middle that didn't get used because there happens to be an odd number of them here. So if I take the 100 from the top, the 100 from the bottom, the 55 in the middle, what do I have that this is approximately? 255. And again, if you'd grouped things a little bit differently, you might not have gotten 255. Maybe you got 275, or maybe you got 225. You're in the same ballpark. Okay. Doing okay?
I have a quick question.
Yep.
How close does it have to be to do approximate?
It really isn't about being how close. It's about whether or not the strategy that you're using is a reasonable thing to do. So like on this one, there are numbers you can't group together that don't make any sense, right? I can't group together 42 and 35 and say that's about 100. It's more like that. Does that help?
Yes.
Okay. Okay, a couple more. 3 more, I guess. Clustering. Okay, so clustering is the idea, and it doesn't work for everything, but there are groupings for which it does work. It works when you have numbers that are all pretty close to the same thing. What nicer number are all these numbers pretty close to? They're all pretty close to 500, right? These are all approximately 500. And how many of them are there? 5. So we will take 5 times the 500, and we will get 2,500. That's clustering. And maybe your kids wouldn't multiply. Maybe they would add 500s together. That's fine too. It's the same thing. Add 2 at a time, you get 1,000. Add 2 more at a time, you get 1,000. You're going to get 2,500, so that's fine. Okay, you are familiar with rounding. That's not a new strategy at all. But let me remind you how it works. You need to know what you're rounding to. And sometimes your book doesn't say. They just say round. That's fabulous, actually, because if they tell you that you get to pick, then you can pick whatever you want. Pick something nice. The easiest thing to round to is going to be the thousands digit, because that's going to give you the most zeros at the end. So let's do it for thousands, and then I'll do it for hundreds just so that you can see it too. So if we do this for thousands place, then we are going to take this 4. The 4 will either stay a 4 or it will become a 5. We make that decision based on the number that follows the 4. It's 7. If it's a 5 and up, we round the 4 at the beginning to a 5. If it's a 4 and down, we leave the 4 a 4. So this is a 7. So what's the 4 going to do? It's going to go up to a 5. So this is 5,000. Do the same thing for the next one. We've got a 3. And we look at the number afterwards. 0 to 4, we go down. 5 to 9, we go up. What's the 3 going to do? It's going to go down, so it's going to stay a 3, right? So when we say it's going to go down, we don't mean it's going to become a 2. We mean the 3,100 something is becoming 3,000, which is down. That's what it really means to be down. Oops, wrong pen, 3,000. And we have 8,000 total. So this is the thousands approximation with rounding. Let's do hundreds just so that we've done it a couple of times because they might tell you on particular problems as well which one they want you to round it to. Oh my goodness, hold tight. There we go. So we're going to round to the hundreds place. That's the 7 and this 1. So with the 7, we look at the number right afterwards, and it's an 8. So what's the 7 going to do? It's going to go up to an 8. Now the number in front, that is the 4, isn't going to change. So it's going to still be a 4. But now I have 4,800 because the 7 became an 8. On the next one, the number after the 1 is a 4. What will the 1 do? Stay the same as the 1. And the 3 in front of it always would stay the same unless there was a need to get bigger and affect it, which is often not the case. So we end up with 4,800 and 3,100. And at this point, we would add, but it would be a smaller number of digits to add, right? These are adding 2-digit numbers really at this point. So we'd have 7,900. Okay, we have one more. The last answer, or the last method, is using the range. We use the word range a lot in mathematics. What we're talking about here is we're talking about if you were to round down or if you were to round up, what would happen? So when we talk about using the range, let's do it with, these are 3-digit numbers, so we're going to do it with the first digit on there. So the first one is what happens if I round everything down. So it's like front-end estimation. I keep the first number and I zero everything out. So it's 300 and 600. So that's 900. And then the upper end of the range is rounding everything up, which means like 370 would round up to 400. That's the next hundreds that's above 370. And the 647 would round up to 700 because that's the hundreds value above 647. And when I add these together, I get 1100. So my range approximation is 900 to 1100. Now, it might feel like, well, that's not very helpful. You don't get one answer. That's true. But what it does, or what it should do for our students, if they can look at something and guess or estimate what the range should be, is that it means that when they add the numbers together long-wise, like they actually add it for the real value, like the exact value, if they don't get a number between 900 and 1100, they've done something wrong. This, in terms of a math sense, is where they should end up getting their number. It's got to be between there. If it's not between there, they've done something wrong. Okay? All right.